which is obviously browsing through a series of quite interesting and innovative figures who operate at the moment at the fringe of architecture, and we somehow kind of browse through them and trying to understand what we can kind of bring up their concepts and tools into our ambit. It's far from clear to us as teachers as well what some of these techniques, concepts, and digital mechanisms will be finally applied to. So let's take it in, and also in this case I'm introducing Sheep T. Iconoclast, who will be to a certain extent around for further questioning during the year. I can announce already that he will give a kind of seminar series on Fridays 11:30 called Bit Streams, together with Ruth Convoy, who's sitting right in the front row here. And a few words about Sheeps, who I find quite interesting in terms of the career it's been going through, particularly in the light of new professional identities we're looking at and work organization issues. That he started as an environmental engineering framework, then went on to UCL and to the computer science department to engage in artificial intelligence work, where he then went on to get interested very much into networks in the photogrammetry department, where he got spotted by Bill Hillier and the whole space syntax research laboratory, and has been involved in a series of programs and programming those tools which Alan Penn was introducing on Tuesday. But I'm not quite clear what he will offer now and what the series of inspirational, but certainly as I gather some consummate tools which could play a kind of generative role in some of the design exercises we're looking forward to. So let's welcome Sheep T. Iconoclast.
Thank you very much. Can everyone hear me at the back? Everyone's all right at the back? Good. Okay, don't want to leave you out. I'm going to talk about something which has kind of generally been labelled the new geometry. And it would be very boring to talk to you about geometry, so I'm actually going to try and interweave it with the kind of design aspect of it. It's just something that's emerging at the moment. It's just ideas that kind of starting to bubble up and actually come out of the kind of science labs. And I feel it's important because it actually affects the way we actually perceive the reality around us. And the first thing I want to do is really kind of differentiate between the concept of the natural and the concept of the planned. So this is a natural kind of landscape. Here's a planned kind of a landscape. There's another kind of a landscape. When we look at that, it's very difficult to actually sit there and kind of describe it and measure it. Whereas, as designers, I think we're very used to working with structures, with certain types of forms, certain types of shapes. They influence the way we work, and therefore the way that design appears. Here's another good one. I love this one, actually. It's great. It's like you can actually see the root system. So, for instance, typical Renaissance-style city, as planned, was the idea of using very formal designs, very formal shapes, circles, rectangles, lines. These are generally known as the Platonic shapes, named after Pluto. Pluto, what am I saying? I'm going mad. Plato. Okay, and Plato basically put them into a rigorous context. So he started off defining the concept of a point. He described the concept of a line. He described the concept of a rectangle. He described the concept of a triangle. And these were seen as pure forms, absolute true forms, which were hidden inside objects. Okay? So, and if you look at, it's so endemic, it's so a part of our life. You see some parents talking to their kids and they're going, oh, what colour is this? It's red. Or what shape is it? Is it round? Is it long? Is it a box? It's like, oh, it's square. Yes. Okay. So to prove this, it's like, what shape's this? Any offers? Cylinder, yeah. Okay. Now, this is the first point, approximation. It's approximately a cylinder. It's not a perfect cylinder, but let's face it, we'd all agree it's basically, essentially a cylinder. So the perfect form is the cylindrical one. Any offers for this one? Familiar object? Truncated cone, exactly. Okay. Now, those are two examples of design forms. Let's take a more natural object. I just happen to have a natural object on me. Okay, so what shape's this? It's a cauliflower. I will pass it around in a minute. Any offers on the shape of the cauliflower? Is it a cylinder? No. Is it a box? No. Right. It's a sphere. Yeah, okay. It's a sphere. It's spherical. It's a weak sphere. Okay. And the point is, you look at that and you can give it an approximation of approximate shape. I'll actually make the shape a bit more obvious now. I didn't realise Adrian's 40 was after me. It's going to have a real surprise. What's this cauliflower doing here? Okay. Natural form. Much more like a sphere. But it's an approximation. It's a way of us imposing some order on the object. Okay. What I'm going to do now is actually break up a piece of the cauliflower and then start passing it around. Okay, so I'm going to pass the cauliflower and the sub-part of the cauliflower around, and I want you to look at them. Okay, so start from there. Okay. Back to the notes. So ultimately, what is it to design? Quite often, design is about imposing order onto a system. So for urban planners, urban designers, there's both the facultative part of design, supplying with water, with power, with electricity, with access, but also it's the process of design actually starts to impose order. So it takes the natural and imposes the unnatural on it. It imposes things like grids. These are not forms that spontaneously arose. Someone has deliberately imposed those forms onto them. And the people imposing these urban grids, these urban forms on, are incredibly affected by the order, the logic, the reason behind Platonic shapes. Okay, another Platonic shape there, the circle. Now what makes these shapes interesting and powerful is the fact that they actually are measurable, they are definable. Okay? So, and this is a very important process. I mean, imagine trying to design a building where you couldn't actually specify any dimension of every object. When you're working with buildings, when you're actually working on the process of making a building, the ability to dimension an object is incredibly important in the whole process. I mean, I'm insulting your intelligence here. So. Now, ultimately, what an awful lot of these shapes go back to is the original prehistory, the idea of the right-angled triangle. And the important thing about the right-angled triangle is it allows you to impose an order on a large area. So by taking a piece of rope with 4 squares, 3 squares, and 5 squares, pulling it out taut, you'll actually get a right-angled triangle. With that, you can actually start to impose a grid on a larger area. You can start to do things like survey. And again, to create an urban system or a building without surveying would be incredibly difficult. And so we can see that these forms are actually imposed even on the most oldest of forms. There we go. Now, what I want to talk to you about is the new geometry. And this is where I get problems, because I'm not too sure how to pronounce this guy's name. So I'm going to embarrass myself and call him Mandelbrot. Now, what Mandelbrot was responsible for is actually bringing to light 2 things. Firstly, he brought to light the whole notion of what's known as fractals, and actually giving it a rigorous definition. The cauliflower hasn't been completely consumed, has it? It's still moving, isn't it? Good. The second thing he did was he also created a new way of doing mathematics. And traditionally, mathematicians were very anti-computers. It seems strange, but they're actually very, very against computers. They saw themselves as actually producing these very pure ideas, very pure concepts, very pure proofs. And in fact, if you actually speak to 9 out of 10 mathematicians, are in fact very lousy at doing manual calculations. There are very few excellent mathematicians that are actually good at doing calculations. And what Mandelbrot did was he actually created this new form of mathematics, a new way of doing mathematics, which is very experimental, where he started to play around with using a computer, much to the horror of his peers. And with that, he started to create new ideas, new concepts. So the reason I'm kind of very interested in this whole area is that use of computers is very key to actually exploring these new ideas. Okay. Now, Mandelbrot began with a series of questions which have kind of been ultimately formulated with the idea of how long would it take to walk on the beach all the way around the UK. So, you know, start from wherever you like, start from there, go there, blah, 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 blah. Okay, if you've got a boat, you could sort of drive it in like 2 days, I think, on a high-speed motorboat. There's a race around England. Okay, but if you actually start walking along the beaches, it's obviously going to take a bit longer. The other question is, if I had enough paint, how much paint would it take to paint all of the UK? Okay? Okay, so when we zoom into this coast here, you actually see, well, in fact, it's actually more wiggly than it appears here. So you'd obviously have to walk further. Now, he discovered an interesting thing. If you take a map, here's a home-serving suggestion. Go out, get some maps of the UK, take them. And have you ever seen these wonderful devices you can have with little wheels that actually count the distance between something? Okay, they're in Tottenham Court Road. I've seen them on that, boring. But you can actually wheel them forwards and actually measure the distance along a path. Great. Now, if you do this for a large-scale map, i.e. one that covers a large area, you'll get one answer. If you do it for a smaller-scale map, like this one, you'll actually get another answer. And that other answer is quite a lot bigger. If you keep zooming in and finding a better map and doing it again, you end up carrying a much bigger area. And the weird thing is that instead of actually saying, oh, well, there must be a true length of the UK, and eventually you'll end up measuring the accurate length. So what you're saying is that as you increase the accuracy, the detail with which you look at it, eventually you'll actually find some arbitrary limit, which is the true detail of the true length of the object. But in fact, what he found was the other way around. Instead, the distance you travel keeps increasing and growing rapidly. Now, there's an interesting way of doing this in a simplistic manner. Let us take an edge of a triangle. So you've got to imagine the triangle is down here. We're just going to take one edge of it. And what you do is you cut the middle third up, and you add in a new 2/3 items. Yeah. So effectively, if you started off with something that's 9 meters long, it becomes 3 plus 3 plus 3 plus 3, 12 meters long. Okay. We then, as the mathematicians say, recurse. We perform the same procedure again, but on the smaller elements. So we take each one of these lines now and divide it up in the same way. Any offers on the new length? So this is like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, in fact, it should be 16. Okay, 16. So here, I've taken a spreadsheet and basically typed in the formula that actually predicts the length of the curve. It's pretty meaningless, but let's just turn it into a picture. Here, by the way, I've actually taken the area of the triangle that was one side of and done the same job. Okay, so this is the length of that triangle as you make it more and more, as you cut it up and as you actually make it with greater and greater resolution. As you can see, it's just shooting up. Right? So you can imagine that at infinity, if you carried on for a long period of time, you'd end up with the surface object, which is infinitely big. It's like, oh, strange. However, okay, so you can see here that the numbers just keep growing and growing and growing and growing, and it just goes off the scale, really. Whereas this one grows, but it actually grows at a smaller rate each time. And eventually it reaches a finite area. And the same thing happened for the perimeter of the UK. If you started walking down to the beach, and started following it around, you can actually find that the beach will get longer and longer and longer. But the area of the UK, the UK is an island. It doesn't cover an infinite amount of space. Okay, so you're going to end up with the walk on the beach down to the smallest detail, down to being really microscopically reduced down, and you're walking over every piece of sand, would actually end up being infinitely long walk. You'd spend the rest of eternity walking around it. However, if you decided to paint all of the UK, you'd actually have a finite amount of paint, and therefore a fixed amount of time necessary to do it. And this is the inherent contradiction inside any fractal. The inherent contradiction is you end up with objects with infinite surface area and finite volume. It seems a contradiction that you can have something that has, on one hand, an infinite quality to it, but also, on the other hand, a finite quality to it. Okay, oh, right, so this is the total area. And you can see here the total area is actually going off to some arbitrary limit, whereas length just goes off to infinity. Okay. Now, there are ways which I won't bore you with now in great detail, but if you actually look at some of the references I give, or in fact this book, Fractal Geometry in Architecture and Design, okay, he actually goes into great detail about how to go off and do this yourself. And in that he gives the way of actually measuring a fractal dimension. Now this is the key element. It's easy to come up with strange systems. It's easy to come up with bizarre ways of creating strange shapes. But what makes fractals interesting is they still have this process of being measurable. Now, if you actually find the fractal dimension of a line, you find the fractal dimension of a line comes out to be 1. In fact, because it has this process of, as you keep zooming into a line, it still remains a line. It doesn't matter how much you zoom into a line, it still remains a line. It actually has a finite length. If you zoom into a point, it's always a point, so it has a fractal dimension of 0. A line has a fractal dimension of 1. A square has a fractal dimension of 2, and a cube has a fractal dimension of 3. And so you have these very interesting objects where, by use of these formulae of fractal dimensions, you end up with objects that are 1.26 for that curve I showed you originally, the Koch curve. Ends up with these objects that are kind of partly two-dimensional and partly three-dimensional. They're actually kind of in between the dimensionality of objects. Okay, I said that. Great. I remembered my words. Great. Now, there are lots of ways of creating fractal-like objects. So you take a cube, you remove the center cube, you imagine it cutting up into 9, you remove the center one, you do the same bits, carry on, and you end up with an object. If you do that in 3 dimensions, you end up with one of these sponges. Okay. Now, how far has the cauliflower got? Who's got the cauliflower? It's at the back. Cool. Now, hopefully, by looking at the cauliflower, what was interesting about this, and again, the other element of fractals is this notion of what's known as self-similarity. Self-similarity is the process where the smaller component of an object actually appears like the whole object. Okay? So, for instance, if you looked at that cauliflower closely, and of course I know you all did, if you actually looked at the whole cauliflower and the smaller cauliflower, what you actually had was a smaller lump of cauliflower actually looked like the whole cauliflower, but just reduced down, to an extent, to an approximation. Remember, we were prepared to call this a cylinder, even though it wasn't an exact cylinder, and equally the cauliflower exhibits fractal-like properties. Even though it isn't an absolutely true fractal, it's a reasonable approximation of one. Again, if you look at the cauliflower and then cut off a branch of the cauliflower and looked at that, again, it would look like the whole cauliflower. And in theory, you could carry on going, but eventually you'd actually reach a limit when you got to about, well, on trees it's about 8. You actually have 8 levels of division between the root and the branch. Okay, so it's always useful to suggest ways of having fun at this point. So let's take an arbitrary shape. Here's something you can try afterwards at home. Take an arbitrary object. Okay, photocopy it. let's say we'll reduce it down by 50%. Okay, we'll copy that, and we'll copy that and rotate it once. Okay, so we rotate it by 15 degrees. We'll then take that and then copy that 2 more times. And we end up with another form. Okay, and then we go away and photocopy that one sheet and perform exactly the same operation. So we reduce it down. Come on. We reduce it down, photocopy it, rotate it more this way, and then produce 4 copies down here. It's a quiet night in the photocopy room, so we carry on working. Okay. So, again, it's now getting to be about 3 in the morning. Okay, and you end up with this form, which is very interesting. I mean, it's interesting because A, it has slight qualities of a natural form. It sort of has a sensation of being a bit willowy to it. And I realised that, in fact, it's actually an awful lot like the kind of patterns of black and white markings you get on certain types of seashells. Okay, that's the final one. Oddly enough, on a computer, this is much easier. Okay, so you end up with this quite interesting form. And all I've done there is done a very mechanical process. Okay, so we tend to have like organic, natural, pure as one end of the spectrum, and designed, rational, logical as the other. But in fact, this was a designed, rational, logical process I went through, but I actually created an object that actually has a fairly organic, natural feel to it. Okay. Ooh, one more. I was working hard. Okay. All coming from an original object. Okay, the next one. So, 2 essential properties of any fractal are self-similarity and there is a logical way of creating them. Okay, this is important. It's not random. We're not talking about randomness here. We're not being chaotic. We're just being methodical. The next step, which Mandelbrot did, was to actually start playing with numbers. And one of the ones he did was he just said, okay, let's take a number, okay, in this case 0.2, and then let's multiply the number by itself and add in 0.23 and just keep doing it. And here you see it kind of starts off 3, 4, 5, and eventually it reaches some limit. So this is what it's happening. And again, we can start with 0.5, and if we do the same process, it actually ends up going down to an arbitrary limit. If we start off with 0.7 over here, it goes off to infinity. If we start with 0.6, it actually stays at 0.6. So, so sometimes by applying this number to itself, you end up with some numbers that go off to infinity, some numbers that go down to a constant, some numbers that go up to a constant, and other numbers that just don't change. Being a mathematician... Oh, by the way, how many people understand the concept of a complex number? 1. 2. We have 2 complex numbers that understand this. Great, okay. Again, in the fractal geometry in architecture and design, it explains complex numbers. A complex number is a number that has a real and imaginary part, and that's as difficult as I'm going to get at this point. It has 2 components. These 2 components could be a position, like a longitude and a latitude. And just as you can add positions to each other, you can actually perform these same things. You can square a position. You can add a constant to a position. And then you can find out whether or not this position goes off to infinity, goes off to 0, or reaches a finite value. Okay, so suppose we actually take these 2-dimensional coordinates and say, so for instance, in here, if it reaches an arbitrary limit, we colour it black. If it's out here and it goes off to infinity, we then give it a particular colour. No, it's around. So out here, actually, no, I've written this wrong, I'm sorry. Outside, it reaches a particular fixed value. Inside, it goes off to infinity. Essentially, the guy said, oh, hang on, I'm getting this strange pattern out, and I can't quite figure out whether or not it's a circle or a square or an oval or some logical pattern. So he got the machine to do all the calculations and plotted them out. And he comes up with this, the Mandelbrot, what's known as the Mandelbrot set. Okay, let's quickly. It's not there. Where's it gone? Oh well, we can't do it. Right, forget it. No, I don't think it's on that disk. No, it's gone. Okay. Play. Now, when we actually zoom in to any one of those points on the edge, you end up with an object. And again, it's interesting because here you end up with an object that looks like the whole object. It has this kind of odd potato-like feel where it has all these blisters growing on it. And no matter how far you zoom into it, you keep seeing the same shape arising again and again and again. So the Mandelbrot set has this concept, has this feel of self-similarity. Because of that, you can actually start measuring its fractal dimension. You can start specifying it exactly. And again, you end up with these forms which actually have this very kind of enigmatic and alien quality to them. They're not purely natural forms, but they're also not purely artificial forms. They actually kind of exist in the gaps between our definitions. Coral reef, maybe? Now, at first I said we started off with a single number and came up with those kind of results. Then I said you can use these things called complex numbers, which actually have two parts to them which you can plot on an image. Finally, you end up with these shapes where you work with polynomials, and this is a polynomial of dimension 3. So again, we're doing this equation bashing. We're taking a number, multiplying it by itself, adding a number, taking that number, multiplying it by itself, going over and over again. And you end up with these fascinating spatial forms. Now this one I actually find quite reminiscent of the effect of water, of the propeller blade rotating quickly in water. All these shapes. Now, you might look at that and say, oh, well, that's a particular shape, you know, and it's a one in a lifetime's chance. It's one of these arbitrary, almost kind of random shapes. But that's not true. This is as much a given shape as a square of a particular dimension is. All you need to know is, what's the formula for creating it? And that's like saying, is it a square or is it a circle? Okay, you need to know what the basis of it is. Then you need to know particular dimensions. So it's like saying, it's a square that's 5 meters long and 2 meters wide. Okay, and then with this one, all you need to know is the particular polynomial that generated it and the particular parameters that were put into it, and you can work it out. However, the other nice property of it is you can reverse the process. By analysing this shape, by measuring its fractal dimension, it's possible to work back to the original numbers that created it. Okay? I actually quite like this one. Has a very interesting quality to it. Now, of course, what's interesting is that the Platonic shapes are the ones that really dominate our design process to an extent. If you go off and you look at any CAD program, you get, you know, it's a cylinder, it's a box, it's a line, it's a polygon, it's a blah, blah, blah. All these very sensible, straightforward Platonic objects for you to design with. You know, we can imagine a future where you actually had all these fractal objects as yet another palette item. And again, they're specifiable down to this level. Okay, so final bit. How am I doing for time? It's not too bad, actually. It's going quite well. Final bit. Another game to play. Take a large sheet of cardboard, cut it up into 4 quarters. Take each quarter and lift one corner up or push it down by a particular amount. So let's say we move it up by 1/10 of its height above the ground, or we move it down by 1/20 of its height above the ground. Okay? Take each one of these quarters you've just cut up and perform the same process to it again. Okay? So again, what we're doing is providing a very repetitive, very mechanical process. And hopefully, So doing this long enough, and you end up with a shape like this. Now what's nice about these shapes is that you can say, oh, that kind of looks mountain-like to me. And then you can go out and say, well, are there any mountains that actually obey this, are actually like this? And this is something that, for instance, people like Mike Batty have done to the formations of cities. What he's done is he's created a process for generating a dynamic city. And then he says, well, okay, I've invented a process for creating a dynamic city. Is this research? No, it isn't. Anybody can invent a nonsensical idea. It's easy. However, what he can do is say, okay, well, I've created this process. Is there a way of measuring the city I've created to see whether or not it's like cities we exist in real life? Okay? And it would be easy. It would be incredibly trivial if all cities were nicely circular. You could sit there and say, I think cities are pretty circular. Yeah, cities are circular. And in fact, I can prove this by measuring the radius of a city. And because I can show that each city has a particular radius, then I'm pretty sure that cities are pretty circular. Okay, so he's done the same thing. He's going, I think digital simulation algorithms can actually produce pretty neat-looking cities. They look right. Is this enough? Is this enough to prove my research is correct? No. So let's measure the fractal dimension of the cities I've created and the fractal dimension of real cities. And he shows they actually have very similar fractal dimensions. So it seems to be that he's actually producing an interesting approximation in form. Okay. Similarly here, you can actually measure the fractal dimension of a city, fractal dimension of a mountainscape. Go out, measure a real mountainscape, find its fractal dimension. If they match, you're actually kind of starting to uncover a pretty interesting process. Here's another one. So by changing the parameters on the fractal, you can generate different types of landscapes. You can do this in all kinds of ways. Right. Imagine we take this board and we have a pen, and then we sit there and say, right, I'm going to colour the top left-hand corner blue, the top right-hand corner a slightly darker colour, and then leave the rest alone. Okay, and then you take each square, cut it up into quarters, and perform the same kind of action on it again and again and again and again. And what you end up with is this very cloud-like, this very kind of fluffy quality of object, very fluffy quality texture. And again, you can do the same thing in 3 dimensions to actually create clouds. There are some very interesting quotes about God, and saying like, is God a geometra? In that he doesn't seem to use a ruler anywhere. Nature isn't made by a cabinet maker because, clouds aren't square. And yet now we seem to be finding the compass and the measure by which God is actually creating the nature around us. Oh, no, it's not supposed to do that. Hang on. Yeah. Slight technical intermission here. Stop moving. Stop it. Okay, so finally I've left some reading up in case you get interested. There's On Growth and Form, Fractal Geometry in Architecture and Design, Fractal Cities by Mike Batty, who I think gave a talk last year. Chaos. Oop. Yeah. Chaos and Fractals. So the Fractal Geometry in Architecture and Design is this one, which you can't see because it's too dark. Let me just give them one. And there's some very interesting examples of this. This guy's gone along and actually looked at various types of buildings and actually measured their fractal dimension. And he does interesting things like, for instance, if you go into a traditional southern French hill village where architects like to have their summer houses and people like to go in the summer, you end up with these very irregular forms. And yet, when people make housing estates, they tend to make very regular shapes. And the question you could start saying to yourself is like, well, supposing I made the gaps between the buildings, the widths of each building a random amount. Would that actually give me a natural feeling form? And of course, what's actually he's done in this book is actually analyse various street plans, and actually said, in fact, you can actually find the fractal dimension of these natural street plans. And so what you could conceptually do is then go out, randomly create these gaps, giving it this natural organic feel, using the same kind of fractal dimension, and you'd end up, theoretically, with something that will only take 6 months to build, but will actually have the feel of something that might possibly have taken thousands of years to evolve over time. Yeah, so highly recommend a bit of reading. The Mike Batty's Fractal Cities is another good example of how to actually use fractals to analyse urban form this time. And of course, the original book On Growth and Form by Darcy Thompson used to be a really big read back in the 60s, but it's kind of no longer part of the kind of standard reading in most schools of architecture, which is a bit of a shame. It's a good book. And finally, for the people that really want to know the real facts about absolutely everything, the Chaos and Fractals book, which is literally big enough to stun an ox. It's a big book, but well worth going through. Okay, so if you give me a chance to have a quick drink, I'll open the floor to some questions. Any questions? Did anyone understand anything I said? Shall I? No, wrong button. I thought there was a dim switch on this one. No?
I just wanted to ask if you were aware of researchers that come from Stuttgart University, which are also using fractal dimensions to measure metropolitan regions and the settlement patterns within there, and these kind of images which look like kind of splashed ink.
Yeah.
And the finding that there's a kind of constant relation emerging between area and circumference, which would otherwise the hermetic figure, of course, would increase the ratio of area enclosed relative to circumference of a city figure.
I mean, I think,
just wonder if
yeah.
you're aware of that research.
I think Mike Batty mentioned something about it in the Fractal Cities book, because it's very much akin of the kind of work he's doing. It might have actually happened after him, but I think it's actually mentioned in that book. It's very much some of the similar process he's going through. So actually, and I think it's an interesting process because, traditional geometry hasn't really had good success with the description of how big cities are and how they grow.
It's exactly also this. There's a kind of staggering is that uniformity about these kind of patterns across various urban centers across the globe in all continents in a way, even though you would with this modernist, as it were, growth patterns.
Yeah.
Of course, totally other than any, let's say, previous historical period, let's say, feudal kind of growth patterns, which breaks down in totally different, more platonic to certain extent. And also, what's very interesting there, not only can you simulate the kind of empirical measures you find, but also laws of how they arrive, how they grow. They not only grow out of the center, it kind of grows out of the center, stops at a certain time, and then small sub-cities kind of grow back against at a certain moment, and you create a certain, you simulate a whole kind of morphogenesis, but only on that level of abstract pattern reproduction. It doesn't not, and the controversy starts when you try to understand what is really the engine or the law which enforces this point by point. What is the kind of, how is the local rule which creates that, enforces that, and what kind of
I think, just to kind of repeat what Patrick just said in a short sentence, he pointed out there's some interesting work in Stuttgart, And one of the things I think that you were saying was they actually came up with this whole process where if you actually looked at the error perimeter ratios, the fractal dimensions of a variety of cities, you'll find that again and again around the world these properties are maintained across many cities. So it seems to imply there are some fractal elements to these cities which are a constant to any kind of urban growth. At this point, things get a bit difficult. And that makes it quite interesting, I think, because you have this process by saying, well, we don't really understand how cities function. We have kind of impressions, we have kind of views. And I think, to an extent, measuring the fractal dimension of various algorithms is a new approach to actually trying to understand the growth in a city. I think lots of arm waving here. I think kind of traditional views of the city tend to be at the stable city, the city having reached a stable state. Certainly people doing transportation planning actually tend to believe that the idea of peak travel when everything has actually kind of evened itself out. And they have this idea of the ultimate city, the climax city, where everything has actually been sorted through. Whereas in fact what they're not quite good is handling the dynamic city. The city that's constantly evolving, the city that's constantly changing, because at that point all their assumptions are constantly being challenged and constantly becoming out of date. Fractals do have this property, do have interesting properties that seem to kind of emerge in cities. But there is this point about saying, how do these properties emerge? A good example of this is some work done in the early space syntax research, where one researcher noticed that if you actually go to the legendary French hill village, you can notice that no new building has ever been created when it's blocked the route between one door and another door. If the route from one door to another door is visible, it's never been blocked off. And so he programmed a computer to generate, to simulate 300 years worth of urban growth, or village growth in this case. And basically these kind of simulated people would come along, start off with a farmhouse or a couple of farmhouses, and then decide to randomly put their house down adjacent to another house, providing that wouldn't block off a line of sight between two main doorways. And lo and behold, for village-sized objects, it would actually create things that looked really effectively village-like. This was the first problem, because back in the kind of early 70s, there was no way of saying, it looks village-like. It's like, it looks village-like, but is it village-like? It's this basic problem. Something might appear like it actually has some kind of content to it, but how can you actually measure it to actually say it's true or not? So one of the nice things about fractals now is he could actually measure the fractal dimension of his villages, measure the fractal dimension of real villages, and actually compare the two together to actually verify his research. The second side of it is that when the village started to grow beyond a certain extent, up to about the level of 1,000 houses, suddenly the village didn't look like a town. These processes didn't look town-like. And so obviously there was another factor entering the arena that wasn't. There was another rule that was adding in later on that people on the ground would be applying when they're designing, when they're actually deciding where to build their houses, but wasn't actually appearing in this early simplistic model for village growth. So yes, and I think as cities, for instance, one good space syntax fact is that if you actually imagine, did everyone see the space syntax stuff yet? Have you actually seen it? Yes, some have, some haven't. Okay. Space syntax starts off by trying to define space. Who knows? And it does that by creating these series of axial lines, these lines in space that help define what a space is. And they discovered something quite interesting, which is, on average, in a small town, it takes on average 7 changes of direction to get from one place to another. If you imagine going from here to, say, Oxford Circus, you go out the door, you turn down the street, you turn again onto Tottenham Court Road, and then you turn onto Oxford Street, and then you get to Oxford Circus, yeah? So you've got like 1, 2, 3, 4 changes of direction to get to Oxford Circus. On average, we take about 7. The strange thing is, no matter how large the city, you ended up being, on average, 7 changes of direction, 7 to 8 changes of direction, at distance from everything else. It seemed to be that the city was automatically regularizing itself, so it never became too complex to move through. Okay. So there are these very interesting properties that actually keep emerging out of real urban objects all the time. But there's still an awful lot of uncertainty about what they actually mean. Yeah, sorry, that's that question. Any others? Anyone fancy running away and doing some photocopying now this second? Just checking. Any good cauliflower recipes? Yes, well, that's it basically, unless there's any other questions. Right, great, wonderful. Oh, one.
Do you have some research about constructibility of these fractal three-dimensional objects?
IBM. Have you seen these automatic milling machines? Have you seen them? They're kind of like, do you know what a milling machine is? Yeah? They're basically, it's, how would you describe it? It's basically a cutting edge that's rotating very quickly. And its position vertically and horizontally and in that direction can be controlled by a computer. And originally it was controlled by a guy turning wheels. And with it, you can actually mill quite complex shapes. But basically, you cut into a large lump of steel. And IBM actually had a numerically controlled milling machine. So this is something you could basically type in numbers to, and it would actually mill out this particular form. The ultimate toy for an architect, I think, just the idea of sitting there and going, print to form. Just print this model for me, and out comes this model. It's like, great, yeah, fantastic. And there are certain programs that do this. And they programmed it with a fractal, and they actually cut a fractal surface into the form. And to an extent, that actually obeys 2 interesting properties. Firstly, it's reproducible. You can describe the form quite easily. And secondly, as production becomes more not automated but de-automated, have you heard about this stuff Levi's do in America, where you can actually get jeans made to your dimensions? You email them your various leg measurements, and they post you back a pair of jeans, for money, of course. They post you back a pair of jeans that fit you exactly. And they can do this because the machines that do the sewing now can just be programmed with your particular dimensions at any particular point. The lasers that cut out the cloth can just be programmed with arbitrary dimensions. And they can actually make one item specially as easily and as cheaply as to make many. I think in the long term it could actually have an interesting process. Much as Bauhaus kind of responded to the fact that you had this mechanical, machine-driven society where you could mass-produce a particular object really cheaply, I think we're going to get to the stage where we can actually mass-produce individual objects as cheaply as mass-producing mass-produced objects. Okay. Anything else? Good. Well,
Thanks again.
all right. I can't think of anything that kind of does it easier. The closest thing I can think of is a spreadsheet. A spreadsheet. So, do you want So what you do is you can type in numbers like, so that's one vector and that's another vector. You can say that equals that times that. That equals that times that. So, for instance, if you want to add them together, you can say that equals that plus that.
I'm sorry, we're going to have to
Okay,
close
okay.
down because we've got to
Well,
start.
I was going to suggest we just adjourn to the bar anyway and we have
Okay.
a quick drink, and then if there's any other questions, they can
Right.
find you in the bar.
Great.
Yeah, I see. So
So that would actually help you do all the,
calculations
and you can play with it at that stage, which is the fun part.
How far into complex numbers do you get? You get me that?
To do a Mandelbrot set, if you can multiply them, that's it. It's really easy, yeah. And the internet is littered with people writing Mandelbrot programs. It really is. It's like there's a secondary school, sort of 8 to 12 area that can do this whole thing. So it's not that difficult.
That's great.
Future cities?
Yes.
Yes, yes. Yeah. Mike Batty gave a lecture last year. He actually works down the street.
Oh, he does, I see.
Yeah, he was in Southampton when he wrote the book, but he's now here.
I see. Fine.
Yeah.
could you show me this book,
This one?
Fractal Geometry in
Hi.
God,
Card. Ooh, have a card.
I write in some Indian journals,
Ah.
architecture journals. I would be interested in writing about the lecture.
That's my day job. Okay.
Information about what should be done.
Well, I haven't really done that much work in the area. I wrote this lecture originally because I wrote the same Masters in Virtual Environments. And part of that was this process of how do you design a virtual environment? How do you actually create something natural looking in a virtual environment rather than very artificial looking stuff? So I had this lecture ready on fractals. The person who's really done an awful lot of research in the area is Mike Batty. And if you want, I can give you an introduction to him. He's the one that wrote the book. So it's a good way of getting in contact with Mike Batty. Ruth would know. Ruth Conroy. What's his phone? If you phone up 387-7050. No, he's at a place called CASA, the Centre for Advanced Spatial Analysis. 387-7050. Oh. Yeah. And ask for Professor Batty. Can I just clear this stuff away?